Hi, so I think the trickiest calculations that they can give you on the paper one are the specific heat capacity latent heat ones, where you have to find the mass rather than the temperature change or rather than the specific heat capacity itself. So I've written a question here for you to have a go at, and then I'll go through it. So student places ice in a beaker. Temperature of the ice is -5 degrees Celsius. The student heats the ice until all of the ice is melted and then stops. 11,000 joules of energy is needed to increase the temperature to 0 degrees Celsius and then melt the ice. Calculate the mass of ice in the beaker. And you're given the latent heat of fusion of ice, the specific heat capacity of ice, and then like a diagram to show what they've done. The only thing I thought is maybe they could have used E, energy, so they could have used P as IV, given you the current, and then used energy is power times time, maybe to get you work that out. But I think this one's hard enough as it is. So pause it, have a go at it. Then unpause and I'll go through it. So the tricky thing with this is you know the two equations, right? Because you can find the data sheet. You know the energy transferred is equal to mass times the specific heat capacity times the temperature change. And you also know the energy transferred is the mass times the latent heat. And it's confusing. Which one are you going to use, right? You can figure out, you've got a temperature change, right? So we've got a temperature change of 5 degrees Celsius. Because it's going from -5 to 0, so the temperature changes 5 degrees Celsius. But what do we use? They've given us here the latent heat of fusion of ice, that's L here, and they've given here the specific heat capacity of ice. Now, the thing is, if you don't know the mass, they can give you these ones where you have to find out, you have to use both the equations. The idea is the ice is going through two situations. The first situation is your ice starts off at -5 degrees Celsius and it's heated up, so energy is supplied to the ice until it gets to 0 degrees Celsius, which is the melting point of ice. That's the first step. And for that step, we're going to use this one here. The energy supplied during this step is MC delta theta, right? Where we've got the temperature change, 5 degrees Celsius. We've got the specific heat capacity of ice here, and we don't know the mass. Then, once the ice has reached that situation, it's then the latent heat that's added to melt the ice. So you get a puddle of water still at 0 degrees Celsius. Because there's no temperature change, the specific latent heat is just mL, and we've got the value for latent heat. Now, the energy that they give here is this plus this. So one of the first things in these questions, if they give you both latent heat and specific heat capacity, is to think, well, I'm going to add them together. But then it can be a bit tricky. So I'll show you what that's going to look like. So I'm saying that my total energy that I've supplied through the whole process is this, the energy MC delta theta, plus this, the energy ML, because I'm increasing the temperature of the ice and then I'm letting it melt. So I add these two values together. Then I'm going to substitute in what I know. So I know energy is 11,000. I don't know the mass. I know the specific heat capacity of ice is 2,108. And I know the temperature change is 5. Plus, again, I don't know the mass. I'm going to put that in brackets because with the pluses and I don't want to get muddled up. Plus the mass times the latent heat. So 334,000. And again, you might still get that and think, well, how can I do with that? I've got two M's in it. But if this was in maths, you wouldn't freak out. So I'm going to do a bit of the sums I can. So I can do 2,108 times 5. I didn't do these in advance, so you get me plugging in my calculator. So I'm going to write it out again. So I get 11,000 joules is equal to mass times 10,540 plus, this isn't changed, mass times 334,000. Now, if I write that again though, so say if I write that like this, right, that's 10,540 M's plus 334,000 M's. That might help you see that what actually I'm going to do in this case is I'm going to either just add these M's together, or 11,000 is going to be equal to M. It kind of take it out and make a little bracket for myself. 10,540 plus 334,000. Right, and then once I do that, I can add those sums together. So 10,540, which is still on my calculator, plus 334,000 gives me 11,000 is equal to M times 344,540 I should have been able to do that in my head. And then I can just divide both sides. So if I write it out here, I've got 11,000 is equal to m times 344,540, and I'm going to divide both sides by 344,540. Those cancel, and then I get mass is 11,000 divided by that, which is already on my calculator. So I'm just going to do 11,000 divided by the answer, and I get 0.0319266 kilograms. They haven't told me any significant figures, so I'm just going to do it to 3. So 0.0319 kilograms, which kind of makes sense. It's about, if I divide that by 1,000, multiply that by 1,000, I get about 31 grams. So that's a reasonable amount of ice. Makes sense for the picture. I hope that helps. Let me know if you want me to come up with some more ones to practice that. I generally think those are the trickiest kind of calculations that you can come across because they're just different from everything else. Good luck.